Uh, Thank you very much for the invitation to speak here. It's really a pleasure. Um, so this is going to be joint work with Scott Sheffield and Terence Tao. So I'll start with describing what a hive is. This is a combinatorial gadget that comes up in the representation theory of GLNC, specifically in computing tensor product multiplicities of irreducible representations of GLNC, but also comes up in the solution of the Horn problem, which is the problem of understanding what the possible spectra are of sums of Hermitian matrices with given spectra. So this is a hive. It's a triangular array of numbers. So given three partitions, or more generally in our case, these will be just real vectors with entries that are non-increasing. But in the representation theory context, these are partitions. So you have lambda, mu, and nu. Then what you do is you write lambda here. So this gap here is 40, the first entry here. The gap here is 30, the second entry. The gap here is 20, and the gap here is 10. And then you write mu downwards. Again, the gap here is 40, the gap here is 30. Reading this from left to right. Gap here is 20, the gap here is 10. And then on the bottom row, you write nu, where the gap is 65, 55, 45, and 35. So because this is non-increasing, restricted to each of these lines, if you take the piecewise linear extension of these numbers, you're going to get a concave function on this line. Similarly, you have a concave function on this line and a concave function on this line. So a hive is a assignment of numbers to the interior vertices in such a way that when you take the piecewise linear extension to the entire triangle, for example, here if I've written 100, 150, 125, inside this I will have to interpolate it with a flat linear function within this with these constraints. And similarly, for every triangle, you interpolate it linearly. So when you do so, you get a piecewise linear function, and this piecewise linear function is supposed to be a concave function. If this is the case, then we say that the numbers written on these interior vertices and the boundary together form a hive. And if not, they don't form a hive. So these inequalities can be, the inequalities that such a concave function must satisfy are called rhombus inequalities. Basically, for every rhombus consisting of 4 points like this, so it could be a rhombus like this, in which case we have that this value plus this value is greater or equal to this value plus this value. So if you see, it has to kind of bend downward. So if you see here 125 plus 120 is less or equal to 100 plus 150. It's in fact less by 5, right? And so this same condition has to hold for every rhombus of every orientation. So every elementary rhombus of side 1 has to have this condition that this plus this has to be less or equal to this plus this. Similarly, for this rhombus, we need that this plus this has to be greater or equal to this plus this. Okay, so these are called the rhombus inequalities. If all of these are satisfied, then when you take the piecewise linear extension to the interior of the triangle, you get a concave surface. And this is the if and only if condition. So these are called hives. And these were introduced by Knudsen and Tao to prove the saturation conjecture for Littlewood-Richardson coefficients. So together with the work of Kleachko, this implied the Horn conjecture, which gave a description of the possible spectra of x plus y, where x plus y are Hermitian matrices of given spectra. So this is an alternative way of writing a hive. So I'll just tell you how this comes up. So basically, we had those slacks, right? These rhombus inequalities. So for every rhombus inequality, you can associate a non-negative positive number, which is the amount of bend, or in other words, in the notation of this slide, the slack would be y plus w minus x minus z. Okay, so this is a slack of a certain polytope, and these hives are points in that polytope. Right? Because if you have a bunch of linear inequalities, then the set of points that satisfy all these linear inequalities form a polytope if it's bounded, and these turn out to be bounded. So these lengths here are equal to the slacks of certain rhombus inequalities, and one can see that if one goes takes a hexagon in that hive and you go around, then when you add this plus this plus this plus this plus this plus this, you will get back to where you started off. In fact, these honeycombs have all their angles to be 120 degrees. Okay, and these lengths, as I said, represent the slacks in the inequalities. So, in fact, one can see that when you have such honeycombs where all the angles are 120 degrees, the difference between this and this is equal to the difference between this and this in length, which is equal to the difference between this and this. Okay, so it's a strong constraint, the fact that all the honeycombs are 120 degree angles. So when lambda and mu n correspond to partitions, the Littlewood-Richardson coefficient is the multiplicity with which the irreducible representation V mu n of GLNC appears in the direct sum decomposition of the tensor product VA lambda n tensor V mu n. It equals the number of hives with integer coordinates and the appropriate boundary conditions. So I already told you how to get the boundary conditions from lambda, mu and nu. You go here adding successive entries of lambda, go down here adding successive entries of mu, go from left to right adding successive entries of nu. So these integer hives are like lattice points in some polytope, right? So the lattice points in this polytope number corresponds to Littlewood-Richardson coefficients. And as we'll see, the volume of these polytopes arises naturally in the randomized Horn problem, which is a version of the Horn problem where you take random Hermitian matrices with given spectra, add them, and ask what is the probability distribution of the spectrum of the sum. So the connection to representation theory of this this question is that so Nusser and Tao proved the saturation conjecture, which is a statement that if you have some scaling integer scaling k, and for some integer scaling k you have this Littlewood-Richardson coefficient that is non-zero. In other words, if you have the polytope of all hives and you scale it up by some k, and then you get there exists a non-trivial there exists an integer point in this lattice polytope, in this polytope, then even in the original polytope you have a point. So the saturation conjecture, which was stated simply that if k lambda mu if c k lambda k mu k nu is greater or equal to 0, then the original Littlewood-Richardson coefficient c lambda mu nu greater or equal to 0. But because of this connection with hives, it turns out that it's sufficient to prove that if the original hive polytope when scaled by k contains a lattice point, then the original hive polytope contains a lattice point. Okay, and this is how they proved the saturation conjecture, in fact. So so there's a lot of interesting combinatorics that surrounds the Littlewood-Richardson coefficient. So they also equal the number of square triangle tilings of certain domains. So you should think of the green part as part of the boundary. They're not actually part of the tiling, the green tiles. And everything else is a square triangle tiling. And if you count the number of square triangle tilings of this domain, it is equal to a Littlewood-Richardson coefficient with some parameters that come from the shape of the tiling, the shape of the boundary. And Nusser and Tao had also used this puzzle formulation, which consists of labeled tilings. And as you can see, there is some kind of correspondence between these puzzles and these square triangle tilings. They're a bit deformed, this triangle lines, because these parallel, these rhombi have to turn into squares, but basically they are analogous. And you can also see a honeycomb sitting inside this actually. So this is one of the hexagons of a honeycomb. So if you just look at the white squares, they tend to form a honeycomb. And this makes it more clear. So in this picture, this is actually a honeycomb corresponding to some integer boundary and boundary conditions where there is a Littlewood Richardson coefficient that is non-zero. So you see here, this is one of the boundaries. The green portion comes here. This is one of the boundaries. So in some form, these are lambda, mu, and nu. In some way of writing, this gray gray thing comes here, and the content of this tableau, naming the number of ones, the number of twos, the number of threes, number of fours, that goes here. So these are all color coded in a paper of Kevin Purvu which I've taken. So you see the number of ones here is seen here. So all the ones, so the ones are first initially dark red, then light red, and then lighter red, and then this color, and those form this last line here. The twos are purple here, and light here. They form the next row, and then the threes, and then the fours. So this is the original, more or less an original little LR's, what people call LR's Q tableau, which is, for example, in Fulton's book, what is used to count Littlewood Richardson coefficients. But this is a proof by picture due to Tao, where he shows that this is actually the same as counting honeycombs. So you see, this looks like a honeycomb, except that it's integer honeycomb, and so you can actually correspond it to this square triangle tiling, where all the lines here are squares, all the vertices become equilateral triangles, and then you have these hexagonal pieces there, but each of these hexagonal pieces can be tiled uniquely using equilateral triangles in exactly one way. So it doesn't contribute to the multiplicity. Okay, so this is like a square triangle tiling. So this is another way of looking at Littlewood Richardson coefficients. So now I'm going to go into the probabilistic part. So the main focus of this talk was to understand the shape of hives. So as I spoke, in the beginning, these hives can be thought of as some sort of concave functions with fixed boundary. So the question we want to look at is what happens when you take a random hive from the polytope of possible hives with some tilting in terms of one of the sides, and what is the shape of such a random hive, and that shape will have some significance for the randomized Horn problem. So now I'll move into that. Okay, so we're going to define this relation lambda plus mu goes to nu if there exist Hermitian matrices A and B with eigenvalues lambda, mu respectively, such that A plus B has eigenvalues nu. So Weil asked the question of determining necessary and sufficient conditions on lambda, mu, and nu belonging to the spectral cone, namely real vectors with non-increasing entries for this relation to hold. So are there any questions so far? So as conjectured by Horn and proved by Klyashko, Knudsen, and Tao, that particular set of possible spectra forms a polytope called the Horn polytope, which we'll call Horn lambda plus mu, which is a set of all nu in the spectral cone such that lambda plus mu goes to nu. So it's this polytope of all possible nu arising from a given choice of lambda mu, and it forms a polytope of given by one equality constraint, which is the trace constraint. The trace of lambda plus the trace of mu must equal the trace of nu, together with a recursively defined set of linear inequalities known as the Horn inequalities. Now there's some exponential set of these inequalities, which they're difficult to describe directly. They can be written down, but they are a bit complicated. But there's a simpler way to look at it from the point of view of hives, because the hive polytope, if you fix just two sides, lambda and mu, okay, then the possible nu for which there exists a hive, that is exactly the Horn polytope. So it's a kind of projection of the hive polytope that we already described. Because you take the hive polytope, you just forget all the stuff that's there above the bottom side, and just note the bottom side. So that corresponds to a projection. So here you have the hive polytope. And then you have this map which basically forgets everything except the third side. And this is the Horn polytope. Okay, so a typical element here is a triangular array, which is called a hive. And a typical element here is simply the values taken by the third side. So we are going to be interested not only in this polytope, but in a certain, not only on this Horn polytope, but on a certain measure that comes on it, which is the probability of observing a particular spectrum when you add two random Hermitian matrices of given spectra conjugated using Hariharan unitary matrices, which are independent. Okay, so you take x plus y, where x and y are random Hermitian matrices chosen independently from the orbits, add them and take a look at the spectrum. So that is going to be some probability distribution defined here on this polytope. So the Horn measure, which I just spoke about here, it turns out to be a piecewise polynomial and was computed explicitly by Fourier and Zubair to be given by the following formula. The measure at the probability density of nu, the third side of the spectrum of the sum, is v of nu times v of tau. I'll tell you what tau is a little later. Divided by v of lambda, v of mu, where these are Vandermonde determinants, v of lambda, v of mu, etc., multiplied by the Lebesgue measure of the hive polytope. Now, the hive polytope is the set of all hives with given boundary lambda, mu, and nu. Okay. So this is exactly the probability distribution of observing nu, where this is the Vandermonde determinant, and tau is the tuple n minus 1 all the way till 1. So it just is decreasing like this. Yeah. For this, I'm assuming lambda is far too lambda. Yes, thank you. So the thing is, the orbits will have a different dimension, right? If lambda and if lambda I equal to lambda I plus 1 or something, the orbits will have different dimensions. So this particular measure won't quite work because you will require a uniform measure of a different dimension. Yeah. So we introduced the relation diag lambda arrow A for lambda belongs to the spectrum and A belongs to Rn to denote the claim that there exists a Hermitian matrix A with eigenvalues lambda and diagonal entries A1 to An. Okay, so this is another relation. It has a counterpart in representation theory, namely, it's saying if you have a Young tableau with shape lambda, is it possible to put a content of A inside it? So this is true if and only if the corresponding Koska number is non-zero in the representation theoretic context. So the classical Schur-Horn theorem asserts that this relation diag lambda arrow A holds if and only if A is majorized by lambda in the sense that one has a trace condition summation A equal to summation lambda, and the majorizing inequality is AI1 plus AIK less or equal to lambda1 plus lambda k for all I1 to IK ordered appropriately. And this is equivalent to saying that A lies in the permutahedron formed by the convex hull of the image of lambda under the permutation group Sn. So you take lambda1 to lambda n, and you permute all the entries. So I'll just put the n in the superscript because I need this n later. This is one vertex, but then you can take permutations of this, of the form where sigma is a permutation. And you take all such vertices corresponding to the permutations, and you take their convex hull. So if this A lies inside the convex hull, then it is you say the diag lambda arrow A. Otherwise, you'd say it's not true. So this correspondingly, it's possible to find Hermitian matrices with spectrum lambda1 to lambda n and trace A if and only if this point A lies inside this convex hull of this permutahedron. So now I'll introduce these Gelfand-Sutton patterns. So one can think of these Gelfand-Sutton patterns as the slopes on one side of a hive. So I've already told you what a hive is. So these are like the slopes on one side of a hive. So they are simpler objects in some sense because the inequalities that define these are simply that this has to be greater or equal to this has to be greater or equal to this has to be greater or equal to this, and so on for every entry. And this has to be less or equal to this has to be less or equal to this has to be less or equal to this, and so on for every entry. So you have these interlacing inequalities which say that, for example, lambda1 4 is greater or equal to lambda1 3, and lambda1 3 is greater or equal to lambda2 4, and so on. So these slopes here, they always lie in between the slopes of the corresponding things below. So these are called Gelfand-Sutton patterns. And this is an example of a Gelfand-Sutton pattern where it certifies the existence of a Hermitian matrix with spectrum 15, 5, -5, -15, and trace 3, 4, 3, -10. So how does it certify this? The constraints that need to be satisfied is that firstly, this bottom row has to be 15, 5, -5, -15. Every successive row has to interlace this previous thing, and because the traces have to work out right, the sum of the entries of this minus the sum of the entries of this have to be -10, and we see that this sum is 0, this sum is 10, so this minus this is indeed -10. Similarly, this sum minus this sum is 3, this sum minus this is 4, and this sum minus 0 is 3. That is just 3. So I'll tell you in a second what's the sort of underlying connection. So it turns out that you have a Gelfand-Sutton pattern of this kind if and only if there exists a Hermitian matrix whose minors have these eigenvalues. Okay, so if I have a Hermitian matrix whose minors are the eigenvalues of the matrix, the next row is what you get when you drop the first row and the first column of the matrix, and then you look at the eigenvalues of the resulting matrix, of which is one less in size, and then you drop the second row and the second column and you look at the eigenvalues. Drop the third row and the third column and look at the eigenvalues, and so on. So if you have this Gelfand-Sutton pattern, it's a certificate that there exists a Hermitian matrix with these eigenvalues of the minors, not just of the bottom thing. And it turns out that this map that takes you from Hermitian matrices to Gelfand-Sutton patterns is a volume preserving map. Okay, so if you take a uniform measure on the orbit of all Hermitian matrices with these eigenvalues, you get a random Hermitian matrix, and you keep dropping the rows and columns in this fashion and taking the eigenvalues, then you get a random Gelfand-Zetlin pattern from the polytope of all possible Gelfand-Zetlin patterns with this as the bottom row. Okay, so this is a volume preserving map. So you start with a uniform measure on the orbit, you get the uniform measure on the Gelfand-Zetlin polytope. This is a result of Berezhnikov. So we will need to be able to produce hives from Gelfand-Zetlin pattern. So given a Gelfand-Zetlin pattern, we will need to produce a hive. As I sort of briefly mentioned, the Gelfand-Zetlin patterns only contain the information about the slopes on the horizontal sides of these hives. They don't contain any information about what is the slope of these sort of things. So that one has to fix. So given a Gelfand-Zetlin pattern, what we can do is we can take a large gap tuple capital lambda, and then write 0 on the top entry of the hive, add this first entry lambda 1 to this entry, call this lambda 1, and then you know the Gelfand-Zetlin pattern. So you kind of along each row you go using the Gelfand-Zetlin pattern, increment by lambda 1 1. Then you add capital lambda 1 plus lambda 2 here, and then you go using the Gelfand-Zetlin pattern, you add lambda 1 2, then you add lambda 2 2, and you get this. Again here you write capital lambda 1 plus lambda 2 plus lambda 3, and then you go along this row by adding first lambda 1 3, then adding lambda 2 3 to that, then adding lambda 3 3 to that, and similarly for this last row. So given a Gelfand-Zetlin pattern and a set of large gaps, lambda of large gaps, you can produce a hive in this fashion. Now, why do you need large gaps and not just any gaps? Because it turns out that if you don't have this large gaps condition, some of these vertical rhombi, the rhombus inequalities can be violated. So you need that large gap constraint. It's some kind of slack, extra slack you need. So this is a schematic description of what the boundary conditions of the hive look like. So these large gaps correspond to these bends on the horizontal axis and horizontal lines. And the rhombus concavity is essentially automatic consequence of large gaps for rhombi that look like this. And for the other rhombi which look in the other two directions, the interlacing conditions take care of the rhombus inequality. So this is a specific, it's actually the same hive that we saw in this first slide. So this hive is I've just written it sideways because we're going to need it in this fashion. This is a hive with boundary condition 40 30 20 10 plus 40 30 10 20 10 goes to 65 55 45 35. So it's written like this. It's slightly rotated, but it's just the same thing. So if lambda mu nu belongs to spec, we say that a hive H has the boundary conditions lambda plus mu arrow nu if all of these things hold. So the hive conditions are the successive cumulative sums of the lambda j. The other hive conditions are the sum of lambda j plus the sum of mu's, and this set of all for the set of all hives with boundary lambda plus mu arrow nu. So this is just saying that the actual entries that you see on the boundary are obtained in some fashion by taking these cumulative sums, which is something we have already discussed. So now I want to introduce a new gadget called an augmented hive. So this augmented hive is the hive we just saw on this side first. So it's a hive, but then you have to paste together a Gelfand-Zetlin pattern to that hive. Okay, and that Gelfand-Zetlin pattern we are going to sort of put in the form of a hive by introducing large gaps. Okay, so we're going to introduce large gaps. So then this is a hive, and so is this. So it's like a double hive, except that one of these hives is secretly a Gelfand-Zetlin pattern. It's obtained using large gaps. So why do we need this? So this is needed because when you add two random Hermitian matrices of given spectra, the probability of the sum is not just the volume of the Hive polytope here. It has that weighting factor that we discussed, V nu times V tau divided by V lambda times V mu. And that V nu on the numerator corresponds to the volume of Gelfand-Zeppelin patterns with boundary nu. Because this is like a weighting. It's like it just weights it, but now we can look at the Lebesgue measure on these augmented polytopes with slightly larger dimension, twice as much dimension roughly. So one can say the following now about these augmented hives. If you take the boundary lambda here, boundary mu here, take some large gaps lambda compared to lambda and mu, and this A is a free parameter, it can be anything. And now you fill in this augmented hive by filling a hive here and a Gelfand-Zeppelin pattern in the form of a hive here at random. So this is now a polytope because there are a number of linear inequalities that will have to be satisfied for this to be an augmented hive. So you satisfy all the linear inequalities and subject to them, choose the point uniformly at random from the Lebesgue measure. Then what you observe here on the middle side, the third side nu, is exactly the same as the spectrum of the sum, the probability of the spectrum of the sum. So this weighting is taken care of when you add this augmentation of a Gelfand-Zeppelin pattern. So that is the purpose of adding this augmentation. So are there any questions so far? So because so it's a result from free probability that if you take lambda and mu approaching a certain profile in a sufficiently nice way, weakly converging to it, then the spectrum of the sum also converges to a profile called the free convolution of these two profiles. So what this is saying is that when you pick a random point in these large hive polytopes, if your lambda and mu are converging to some continuum profile in some nice way, then that what you observe in this third side here also converges to some profile. So although you're choosing this as a random point in some polytope, it is not truly random in the sense that as a limit of n tending to infinity, it converges to a deterministic profile, this in probability. So our question is this true more generally, not just for the middle side, but is it true for general points in the hive also? And so we are not going to be able to prove this in general, but we will prove this when lambda and mu come from a very specific distribution called the GUE ensemble. So these are the eigenvalues of Gaussian matrices. Okay, so if you choose a Hermitian matrix by choosing each entry to be Gaussian, and up to that, apart from the Hermitian condition, it is independent, the entries are independent, then that's called a GUE ensemble. And we allow some scaling by a positive number, which is not so important. But just to give the normalization conventions, we define a GUE random matrix to be a random Hermitian matrix M, where this xi ij equal to xi ji conjugate for I less than j are independent complex Gaussians of mean zero variance 1. Xi I are independent real Gaussians of mean zero variance 1, independent of the xi ij for I less than j. So it is known that the spectrum of this GUE has this measure. The eigenvalues of a GUE are given by some universal constant depending on n, some constant depending on n, sigma to the minus n squared, where sigma is the scaling factor for the GUE, times e raised to minus the Euclidean norm of lambda squared divided by 2 sigma squared n times the Vandermonde of lambda whole squared. Because here I'm taking A to be a random matrix where A by root of sigma squared n is a GUE. So this is basically scaled up by root n, it is also scaled up by sigma. So this is the kind of GUE matrices we'll be looking at. So it turns out that if you look at the histogram of eigenvalues, that converges to a semicircle. This is related to Wigner's semicircle law, which is true in greater generality. But this is a fixed shape, basically. It's got some random perturbations, but it is basically a fixed shape, and the histogram of eigenvalues follows the semicircle law. So if you count the number of eigenvalues in a particular box, it is roughly given by what the semicircle predicts. So if you take a delta lambda, a small interval here, how many eigenvalues is roughly the area of this rectangle. And this is a semicircle. This is something like sigma 2 sigma root n. This is something minus 2 sigma root n. So with our normalization, it's going to be perhaps there's going to be no root because we are multiplying by root n. Okay, so our question is now this: suppose you take this random augmented hive, not with fixed sides lambda and mu, but with GUE eigenvalues lambda and mu. This is essentially coming from some other curve with some slight perturbations. It's not the semicircle curve because this is the histogram of eigenvalues, whereas what the curve that you will see here is not the histogram of eigenvalues, but rather the cumulative sums. Okay, so it's some other curve that is, of course, related in a deterministic way with the semicircle. So you have these profiles here and here, some curves here, and you're asking what is the shape of the hive, or does it even concentrate? So we know through free probability theory, and for the Gaussian case, we know have an easier argument to see that this here also you should concentrate. It just follows from the semicircle law and the fact that two independent GUE matrices add up to a GUE matrix. But we want to know this more generally here, whether you have concentration. That is what we will talk about. So this augmented hive is this object where you're taking the union over all lambda mu. It's a cone now with some measure on it, because this lambda and mu are not fixed. They're variable. They're varying inside the spectral cone. And then this is some large gaps, which is to be actually, strictly speaking, determined after lambda is determined, because it has to be large compared to lambda. But the thing is, the data distribution here will not depend on this lambda at all, so it doesn't matter. As we are only going to be talking about the distribution of the hive part, not of the Gelfand-Zetlin part, which is actually easier to understand. So, so this turns out to be the measure on the augmented hive, because for lambda and mu, you have some measures coming from the GUE, and then this basically the volume, once you fix lambda and mu, the volume of this augmented hive ends up being roughly V lambda times V mu divided by V tau squared. So it's the same as the product of two Gelfand-Zetlin patterns, polytopes. This is just the probability measure on the augmented hive. You don't have to look at the details. It's got sections which are hives here and hive polytopes here and Gelfand-Zetlin patterns here, but we're taking the union over all possible nu and a. When you fix lambda and mu, this is actually a union over slices. Each slice is an augmented hive of the kind we described, but we are allowing a and mu to vary in this augmented hive. And actually, we are now allowing lambda and mu also to vary according to GUE eigenvalues, but that is essentially constant. with some mild fluctuations. So our main result in this talk is the following concentration bound. If you let sigma lambda, sigma mu be greater than 0 and fixed, and let H and gamma be augmented hive, random augmented hives with these boundaries, then for any vertex T in any point T in the hive part, we have the variance bound. Variance of H of V is equal to little o of n to the 4. Now it turns out that the values themselves are of the magnitude of n squared. So when you say that the variance is little o of n to the 4, that's the concentration result. It says that the fluctuations are little o compared to the value. Little o1 compared to the value, little o of the value, as n tends to infinity uniformly in V. So informally, this asserts that the randomly selected hives have an asymptotic limiting profile, at least in a subsequential sense. So we aren't saying anything about the mean at this point, so we can't say it has an asymptotic limiting profile, but there exists a subsequence that has a limiting profile, in the sense that it converges in probability along that subsequence of n, some subsequence of the natural numbers. Are there any questions regarding the main theorem? So here's a picture of a simulation. This is an actual simulation of a random hive done with n equal to 250. And as you see, you get this nice smooth structure. So this is this concave function that I said the hive is, and this is a nice smooth structure. And you see here that the third side is √2, roughly √2 times the height of these two hives, these two boundaries, this boundary and the one that is hidden. And that is because if you add two random Hermitian matrices with unit variance, what you get is a GUE with √2 as the standard deviation. So the standard deviation of the sum of two independent GUEs is another GUE but scaled up by √2. That is why you see this √2 factor. This is simply because if you take two variance 1 Gaussians which are independent and add them, you get a variance 2 Gaussian. So you see, you get this slightly larger thing here. This simulation was done by Alok Gangopadhyay, who was a postdoc at TIFR. So in some other work with Sheffield, we proved a large deviation principle for the hive part of augmented hives in the L infinity metric with fixed boundaries that were C2 and strongly concave. But the result of this talk does not directly follow, because whether those rate function minimizers in the large deviation principle are unique is not yet known. So while we have a large deviation principle which says how likely it is to observe a hive in a particular Borel set of L infinity of T, we don't know that the rate function minimizer is unique. So in principle, you could have the behavior of having a large variance. So I'll now quickly describe some of the methods of proof. So basically the idea is this augmented hive polytope is a bit difficult to manage. So instead what we do is we are going to take the product of two Gelfand-Sutlin polytopes and get a simpler polytope, which is GT lambda cross GT mu. And this is going to, via a map, a nonlinear map given by the octahedron recurrence, is going to map onto the augmented hive polytope. Now this is easier to understand, so we'll understand this, and this is going to be a Lipschitz map, and we're going to show that this Lipschitz map preserves the concentration properties in some sense, or has some weaker concentration properties, which is still good enough to prove what we wanted to prove. Okay, so this is a pair of Gelfand-Sutlin patterns with lambda and mu, and turned into hives with this large gap condition gamma. Okay, and once you fix this side, then this side gets fixed and this side gets fixed. That's not so important. Basically, these two Gelfand-Sutlin patterns pasted together by the side, and you do this octahedron recurrence, or this map, and you get an augmented hive of the kind we're looking for. So these are actually hives which have been converted from Gelfand-Sutlin patterns in the way that I mentioned earlier. Okay. So these have these large gaps, these initial product of Gelfand-Sutlin polytopes. The points in these product of Gelfand-Sutlin polytopes look like pairs of Gelfand-Sutlin patterns with their common side. So this octahedron recurrence is actually a map of the lattice points in the pair of Gelfand-Sutlin polytopes to the augmented Hive polytope lattice points, and in particular, it's a bijective map, and this implies that it's a volume preserving map from the entire polytope, which is GT lambda cross GT mu going to the augmented Hive polytope. So this is a volume preserving map. So if you want to prove concentration in the latter, it's good enough to prove some good concentration properties in the former and prove that Lipschitz map does not alter things too much. Or Lipschitz map has good enough properties that preserves the concentration. Okay, so it turns out that this octahedron recurrence has a form involving the maximum over certain linear functionals. So it's really so every entry of this map, for every entry in the augmented Hive, you can ask, okay, what is the, so this is a value taken by a pair of Gelfand-Sutlin patterns, and that particular value has this form. So this Hive, the value of a Hive vertex is the maximum of a set of linear functions of the pair of Gelfand-Sutlin patterns. So it's a convex map in particular. And these individual linear functions are in fact given as from matchings of certain excavation hexagons. So this is the pair of Gelfand-Sutlin patterns turned into hives, and this is a kind of, for this vertex here in the augmented Hive, it's only this portion that matters in the pair of Gelfand-Sutlin patterns. And how does it matter? Those W of G1, G2 that I just wrote here, this is a matching, the weight of a matching in this excavation hexagon. So it's like what matters is the maximum weight matching in this excavation hexagon. So if you ask for a different vertex in the augmented Hive, a different excavation hexagon will come. What I've done here is when you take a matching of this excavation hexagon, I've color coded the edges by putting lozenges or rhombi on top of the edges. And depending on the orientation of the edges, as you see here, the edges have three possible orientations. The colors are chosen to be red, green, or blue. Okay, so this is yet another perfect matching. And so these are actually from another paper of mine with Alok Gangopadhyay. So he did these simulations of these random matchings, these maximum weight matchings that you get from these random Gelfand-Sutlin patterns. This is for n equal to 10, and this is for n equal to 20. And we believe that these things, if you look at them, they look like some 3D shapes, right? Because they stick out of the page in some sense. And we believe that that's a way of associating height functions with such a tiling. And we believe that these height functions also will have some kind of concentration property, that they converge to fixed surfaces, but this is not something we can prove currently. This is for n equal to 50, and this is for n equal to 100. So you see, we are observing some kind of limit shape. It seems to be, at least empirically. So how do we actually prove this concentration bound? It turns out that if you have a supremum of such functionals W, and the base measure is a log concave measure, meaning the density is the logarithm of a concave function, then such an inequality follows. So instead of proving the variance of the sup of W, which is this Lipschitz map per node, you can actually just look at the individual Ws and look at their variances and control them. So it boils down to controlling the variance of the individual linear functionals. You don't have to look at that convex functional. But even that requires a fair amount of work. You require some sort of correlation decay bounds for the eigenvalue gaps in the interlacing structure of the minor process or of the minors of the Gelfand-Sutherland pattern from the random matrices. So I'm almost done. So so in view of this lemma, it suffices to obtain some variance bound, and so that we indeed obtain, and then this thing follows. There are some technical difficulties because these covariance results hold only in the interior of the triangle and not close to the boundary. So there are some other relatively crude estimates that allow this to work, but they are based on some correlation decay bounds of Cipollone, Erdős, and Schroeder for the GUE matrices of a single layer, single line in the Gelfand-Sutherland pattern. So in follow-up work, we have shown that this subsequential convergence that I just described is actually a proper convergence. It converges to a limit shape, the Hives, and these are obtained by some by variational sort of characterization of the limit. It's based on an idea of Sheffield of getting a new kind of surface tension, and then we get this result that the limit of the expected value also converges. So what I just showed in this, what I just described in the talk was to prove that the variance tends to 0, but this result also says that the expectation suitably normalized converges to a fixed number. If you have both the convergence of the expectation and the variance tending to 0, for these log concave measures, at least you get convergence in probability. So this gives the limit for the Hives. So there are some open questions which we still are interested in. What happens when you look at the real value, the integer valued Hives which come up in representation theory rather than the real valued Hives that come up in the Horn problem? And do these local statistics for this GUE Hive process converge to some known limit in a probability sense? And do you have concentration for random integer valued Hives? So I'll stop with this. So thank you very much.
Questions? I have a question. So suppose you just take one matrix and you don't specify its spectrum, and then you take a random Haar thing and conjugate it, and then you take the sum. So now this lambda is not...
Take the sum of what?
Sum of this matrix and its conjugate.
Oh, okay.
So it's like lambda is random, not fixed. Mu is also lambda. I mean the other matrix.
See, but these are Hermitian, so you'll get some real matrix in the sum, no?
Yeah, take Hermitian matrices, yeah.
Okay, so you take the...
Do we know how the distribution of this sum will be? I mean, can we use this? So what I'm saying is you don't, so you're taking, you're fixing lambda and mu, right? And then you're taking sum.
Yeah.
But I'm saying lambda equals mu, but lambda itself is random. Is it known what the...
So the spectrum of the sum in any case can be computed in a limiting sense using free probability. At least there is a procedure. It's not
Right.
Always...
That's when the two matrices are independent, right?
The matrix, oh, you want the, but the, I thought you were saying the spectrum is the same, but the conjugation is independent.
Yeah.
So the spectrum can be the same or different. That doesn't matter. The matrix. So
oh, you're saying it.
The conjugating unitary matrices have to be independent.
Okay.
That is the thing.
Okay, thanks. Any more questions? Okay, if there are no more questions, let's thank Hariharan.